Okay, so for solving problems with SOH CAH TOA, I think we're fairly familiar with this. It's only for right angled triangles where we're going to apply those sine is opposite over hypotenuse and so on. The thing that we haven't talked about as much, that's kind of a review for us, is sine law versus cosine law. So just to remind you about these formulas here, we have A over, let me just use my stylus here, it doesn't seem to be working. A over sine A of capital A. Okay, people that are walking in late, sit down quietly and pay attention. Okay, A over sine A is equal to B over sine B is equal to C over sine C. We only ever use two parts of this formula at once. So we'll use one individual part. You should also remember that lowercase represent sides and uppercase letters represent angles. Okay? There's two cases when we will use sine. And both of those cases, what I should be looking for is a side and its opposite angle pairing. Okay? I want to know a side and I want to know that it's across from an angle. Anytime I have that little match, I can use sine law. So either that can happen when I have an angle and two sides, and this angle must be opposite to one of the two sides. And I can also do it when I have two angles and one side, because if I have two angles in a triangle, I should be able to find the third. So anytime I have two angles, I can always find one that's across from the one side that I know. So if I have angle, side, angle, that kind of idea, two angles, one side, I can always find the third if needed. But I still need that angle and its opposite side pairing. Okay, cosine law has kind of like two formats. One of them is just a rearranged version of the other one. So we have a squared equals b squared plus c squared minus 2bc times the cos of angle A. And then if I rearrange this, so this is going to be used for finding a side length because it already has like a side length isolated for us. Or if I rearrange here, we will get this formula, which is simply the rearranged version of the one above, and this one is useful when we're looking for an angle and we have all three sides. So the two cases where we'd use cosine law, which correspond to these two formulas here, are if I have two sides and what we call a contained angle, which is between the two sides that we know. Sometimes it's also called an included angle. So essentially I have side, angle, side, the sides bordering the angle that I know. And that's when I can use the first formula. I can use it to solve for a third side. Or I can use the second formula when I'm looking for an angle and I have all three sides. So three sides would be known. Or in other words, side, side, side. Okay, so I'm going to use formula number 1 when I have this, and formula number 2 when I have the three sides. Okay, of course, I can always use either one of these and isolate for what I'm looking for. That's always a possibility that we can do that. Okay, sine law and cosine law do work in right angled triangles. However, I think SOH CAH TOA is just like the more efficient method of us solving for an unknown when it's a right angled triangle. But if you happen to use sine law or cosine law, you can still use those within right angled triangles. However, it does not work in reverse. I can't use SOH CAH TOA in non-right angled triangles. Okay? All right, so we're going to try an example. We have Jonathan. He's standing 10 meters away from a tree. He looks up, so this is an angle of elevation when you're looking straight and then you turn your gaze of sight upward. And he notices that angle of elevation to the top of the tree to be 60 degrees. Determine the exact height of the tree. So exact meaning, and notice that the angle is 60. We should be thinking special triangle. So when we say exact, we're thinking back to our special triangles. There will be some cases where you will not be able to find exact values. If it doesn't deal with 60, 45, and 30, or one of their obtuse angles like 120 or 150, then I won't be able to find exact values. So I wouldn't ask you for that unless you can actually find it. Okay, so we have a tree. It's beautiful, I know. So nice. And Jonathan's over here. And you have to imagine, like, if I'm standing over here and I'm looking up to the edge of our classroom, my straight line of sight and how my line of sight changes as I look up to the edge of the classroom, this angle at me is my angle of elevation. So I'm looking straight and then I'm looking up to the tree or to the edge of our classroom or whatever, and the angle at me is that angle of elevation. So looking straight, and then we turn our gaze up to the top of this tree right here. I didn't do that line great, but you guys will just add on to the tree a little bit there. That angle of elevation, that's going to be the 60. Okay, so here's our line of sight, and this is our 60. Okay, now there's one little jump in our thinking, in our common sense that we need to make here, and I know that this is kind of like in a perfect world kind of idea, but we're going to kind of assume that if the tree is standing up, that it's at a 90-degree angle to the ground. Okay, so that's a little jump in our common sense. For sure, if we're talking about like a lamp post or something like that, we would want that thing to be at a 90-degree angle. Otherwise, it's going to eventually fall, right? Okay, and what else do I know? I know that this is 10 meters. Okay, so there's a couple different ways that I can solve this. If I'm looking for the exact height of the tree, we're going to call that x. I can set up a trig ratio here, or I can use a scale ratio with my similar triangle. Okay, so whatever works for you is fine, but let's suppose that we don't know how to use scale factors. We just know how to use SOH CAH TOA. So this is going to be opposite to 60, and this will be adjacent. So I'm going to apply tan here, which is opposite x over adjacent, which is 10. Now tan 60. If I know my special triangles, I should be able to replace tan 60 with its actual exact value. So just to remind you guys, hopefully we know these at this point, but if you forget, we'll draw out our special triangle here, label 1, root 3, and 2. And the tan of 60, I should be able to find this just by looking at 60 as my reference angle and finding opposite over adjacent. Okay, so we end up with an opposite over an adjacent here, which is root 3 over 1. So I'm actually replacing tan 60 with its exact value from the special triangle. Okay. Alternatively, if you notice that this triangle is kind of set up similar to our picture over here, you can see that the scale multiple is 10 to get from 1 to 10. So I can take this guy and do a scale multiple of 10 to get our x. So a couple different ways that you could have done this. All right, so I've got root 3 equals x over 10. To get x by itself, I just want to multiply the 10 up, and it becomes 10 root 3. And our unit of measurement, which we will always indicate if we can, if the question tells us, is 10 root 3 meters. Perfect. And quick therefore. Any questions on this one? Pardon? If it's like a word problem, I think we should just make sure that we interpret our answer for that. Cool? Not too bad? Any questions before we move forward here? Okay, can I scroll? Yeah. Okay. It's just like applications. It's all one. It's 2 sections in your textbook, but we're going to do it together. Okay, 2 wires are attached on the opposite side of a tree to stabilize it. Okay, so just to simplify this, I'll just do our tree as kind of like a stick right here. That's going to be our nice little tree. I've got a wire, one on one side and one on the other side. It says it's on opposite sides. So stabilize and stabilize. And the first wire, we can call this wire number 1, is attached at an angle of 30 degrees to the ground. So the ground and the wire make an angle of 30 degrees. The wire on the other side, let's call that wire number 2, is attached at an angle of 45. So that's between the wire and the ground. Okay, and we are also given the height of the tree. It's 150 centimeters. Find the exact distance between the 2 wires. So I want to know how far is this wire from the wire over here. Okay, and again, the tiny little assumption that we're making here is that this tree is perpendicular to the ground. Okay, if you're ever not sure, you can always ask. All right, so I think we know our other 2 angles. So if I am just looking at this left triangle over here, we'll call this triangle number 1. My other angle up here is 60 degrees. And then in triangle number 2, that has wire number 2, this angle up here is 45 degrees. Okay, so I have an isosceles triangle over here. This guy in triangle number 2 should be equal to this guy, right? If I have opposite angles equal, I know that this and this also have to be equal, right? This is like our 1, 1, root 2 triangle. So if my tree is 150, can somebody tell me what this distance is right here? Also 150. So we'll call this x, can be 150 centimeters. This one can be y, and we'll call this one z. Okay, zoom in a bit here. So if this angle and this angle are equal, I know that this side and this side must also be equal. Okay, isosceles triangle. All right, so to find this y here, I think maybe we can just use the idea of scale factors, right? So if I set up my similar triangle, my 30, 60, 91, we know the side measurements of this are 1, root 3, and 2. And notice that I set up the 30 in the same location that I have the 30 in my triangle in my question, just so that I can see what this scale factor is. So what am I doing to get from 1 to 150? What's the scale multiple here? See? We're multiplying by 150. So could I potentially take root 3 and multiply it by 150 to get this bottom length here? Okay, so 150 root 3. Agreed? Okay, so we're just using the idea of scalar multiples here to find that missing element. And what is the relationship between x, y, and z here? How can I find this full length? Yeah, so z is actually equal to the length of x plus the length of y. So here, if we just sub in x plus y, we get this. And you may see some of your worksheets or answers express this in simplest form, which is common factored form, just by common factoring out the common 150 in these terms and writing it as 150 times 1 plus root 3. Okay, so I think that would be probably the simplest and most precise answer. Okay, this is just common factoring here. This is the exact distance right here. Yep. So exact just means no decimals, right? Did we use decimals? So we did it. Okay, probably quite a few different ways that you might have been able to reach this answer. You can also set up SOH just like I showed you in this first question up here, and replace any values that you get, such as tan 60 or sine 60, whatever, with their exact values from the triangles if you don't feel super confident using scalar multiples with your triangles. Okay? Any questions on that one? So many? Ask them.
No, I just have to think. Oh, whoa.
Just have to think through it?
Practice.
Okay. Okay. Can we scroll? All right, let's go. Oh, I didn't realize that this was later in the lesson. Okay, so we already wrote this above, so I don't think we need to rewrite it. Sine law, we're going to use when the big thing here is that we need one side and opposite angle pairing at least. But I listed the scenarios for you guys above, so we're not going to recopy them. So anytime you have one side and its opposite angle pairing, you can either have an additional side or an additional angle, but that is kind of what I'm looking for to decide between sine law and cosine law. That's the big thing that I would be looking for. Yep, Maureen? Yeah, so I can draw you guys a picture here. So let's suppose I have A, B, C, and these sides are labeled across from their angle with the lowercase letter measurement, or not lowercase letter measurement, but with the lowercase letter. So angle B should be across from side B, angle A, capital A is across from side little a, and so on. Okay, so what I would need to know in order to use sine law is, suppose this is 40 degrees. I would need to have a pairing here. Let's say I know this. And I would need to know one other angle or one other side in order to use sine law. But I need at least A, angle A and side A, or angle B and side B, or angle C and side C. Okay, and one additional piece of information. Okay? Sure, so if I know that C is 31 degrees, then I'm good to go for sine law. Okay? And I can always find angle B if I have two angles in here too, as well. Okay, so that's the big thing that we want to look for. Cosine law has a bunch of different varieties. These are essentially, just to understand these guys, you'll notice that angle A, the first thing I start with in this cosine law is side A, and then I use B and C in the rest of the formula. If I'm doing angle B, I want to change this first thing to side B, and then I use A and C in the rest of the formula. And if I change this to C, this is side C right here, and I use side A and B in the rest of the formula. So it changes according to what side you have there. But really, guys, you only really need these top two formulas here, because I can always just relabel my sides to work with my formula, right? Whatever I'm looking for, I'll call that angle A. And then I'll call the other two things B and C. Okay, or if I'm looking for side A, I'll call that, or if I'm looking for a side, I'll call that side little a and label the other two B and C. Okay, we discussed when we use these, so I don't think we need to go over that. We did those above. But essentially, if I can't use sine law, I'm using cosine law. So if you don't have that angle and opposite side pairing, we revert to cosine law. So 3 sides or 2 sides and 1 contained angle. Okay? All right. So Pam, Stephen, and Rachel are standing on a soccer field. Stephen and Rachel are 23 meters apart. Okay, so well, how else can we have 3 people standing? Any 3 points are going to make a triangle, right? Yeah, that's true. But we know the question gives us a little bit more information that says that they're not in a straight line. But yeah, they could be standing in a straight line. So we have Pam, Stephen, and Rachel. We know that Stephen and Rachel are 23 meters apart. So that's side little p, because it's across from angle P. From Stephen's point of view, so if I'm Stephen and I look from Pam to Rachel, so let's say Karen is Pam, and Rachel is Paige. If I look from Pam to Rachel, my angle at me is 60 degrees. So the angle at Stephen when he looks across from Pam all the way to Rachel, that forms an angle of 60 degrees inside there. Okay, and then similarly, from Pam's point of view, if she looks across and she sees, okay, Stephen all the way to Rachel, she's going across an angle of 45 degrees. So that's her line of sight over at her. Okay, I'm going to label this side little s and side little r. Those are our unknowns right now. So boom, part A done. We sketched a diagram. Sweet. Determine the exact distance from Pam to Rachel. That's side little s.
So would you use like B?
So if I have an angle and its opposite side pairing, see how we have the 45 and its opposite side? Automatically I want to go sine law.
Would you want us to change the
So sine law, yeah, exactly. So sine law is just saying the side over the sine of its opposite angle should equal the other side over the sine of its opposite angle. So I can make A, B, and C anything I want, right? Here it's P, R, and S. And we only ever use two parts of this formula at once. Okay, so side little p is 23. Angle P is 45 degrees. Side little s, that's our unknown. And angle S is 60 degrees. Okay, in order to get S by itself, I'm going to multiply up the sine of 60.
Should you use the special triangle?
Yep, we're going to do that as well. So we're not calculating on our calculator yet. I'm just isolating for S right now. And because I have 60 and 45 as my angles, these both come from special triangles. So if you need to draw out your special triangles, you can. But I want to find the sine of 60 exactly. And, oops, 45. And I want to find the sine of 45 exactly. So sine of 60, let's start with that one. What is the sine of 60 if 60 is our reference angle? Louise?
Root 3 over 2.
Great, root 3 over 2. So I'm going to replace sine of 60 with root 3 over 2. And I also want the sine of 45. Close? Yeah, 1 over root 2. So that's like opposite and hypotenuse. Doesn't matter which 45 you choose as your reference. So that will be, oops, 1 over root 2. Okay. I don't know about you, but we don't like fractions within fractions. So I want to just take my bottom fraction here, and I want to flip and multiply. So we can consider this, we can kind of multiply this 23 in here, but I do want to flip and multiply the bottom fraction. Okay, that's what we do when we divide fractions. We flip and we multiply. All right, so I think the bottom part's pretty easy here. We're going to have over 2. 23 and 2 can't be reduced, so I can just leave that. Root 3 times root 2. Can somebody remind us what that's equal to? Yeah, Ivana? Root 6. Very good. And do I have any perfect squares inside of 6 or anything that I need to reduce here? No. So I think this is our exact value right here. Maureen?
Why was it 23 times 3 over 2?
Because the exact value of sine of 60 from our special triangle is opposite over hypotenuse, which is root 3 over 2. No problem.
Wait, what happened to the, why did you 3 by itself now? The root 3?
What do you mean, why is it by itself?
Like how did it get, like how did the under 2 and like the 1 go away?
The over 2 is still there. It's right there. Okay, I'm just multiplying this 23. So if we think of this as 23 over 1, I'm doing 1 times 2 to give me this 2. And then I'm doing 23 times root 3 to give me 23 root 3. So I'm just merging those two fractions by multiplying. And then I flip and multiply the bottom part. Okay? The second part of this, part C, asks us to determine the distance from Stephen to Pam. And it does not ask for an exact distance. So the distance from Stephen to Pam, this is little r. So that's B. We'll put that over there. And we'll do C. What? Oh, that's sad. Can I find, if I know two of these angles, 45 and 60, can we find angle R really quickly? How can I find that? Elise?
Add them together and subtract from 360.
Close, not 360. What do we,
180.
180. Okay, so can we do 180 minus 45 and minus 60 quickly to find this guy?
Is it like
75? Awesome. Okay, so that gives us 75 there. I'm going to use this side and its opposite angle pairing that was given to me in the question. Just in case I made a mistake on part B, I want to use that. I don't want to use that to calculate my part C if I can avoid it. If I can't, then I will use it. But if I can avoid it, I'm just going to use this pairing right here. So it's going to be little p over sine p equals little r over sine r. So it's always the side and its opposite angle pairing. Okay, p and angle p, side little p and angle p are given in the question. And we found angle r by just subtracting the two other angles from 180. So that should be pretty straightforward. This one doesn't ask me for an exact value because I can't get an exact value when I have the sine of 75. So that is partially kind of the reason why we must use a rounded number here. So sine 75, we're going to multiply that guy up to get the r by itself. And these will cancel. And then I'm just going to have you plug this into your calculator and calculate. So you're going to do 23 times the sine of 75. If your calculator opens a bracket, you're going to want to close your bracket and then do divided by sine of 45.
You got that formula off the sheet, right?
Yep, the formula is just sine law. What'd you get?
31.41.
141?
31.41.
Oh, 0.41. Okay. Everyone else? Okay, we've got two different answers here.
You didn't do it over side 45 then. I got that before.
Okay. So 34 point,
31.
oh,
30, yeah.
0.42? And units of measurement are meters. Great. Okay, you guys ready for a 3D one? Do we need to take a little break before we go into 3D?
I think we always do.
You always need a break? So I have made you a lovely model over here to kind of show you what's happening with this, because this is not the greatest picture. But here's my antenna. It's a cup of pencils. We have Elena's house, this bell over here, and we have Sam's house. You're in this question. And it's a pencil sharpener. And I've kind of drawn out what we know here. So we know that this bottom triangle, the one that's flat on the ground, is a right angle. We can see that right here. Okay. We also know that the angle at Sam's house over on the ground, feel free to move up if you want. We know the angle at Sam's house on the ground, so we're still talking about the 2D triangle that's on the ground, is 50 degrees. We also know that Sam's house and Elena's house are 120 or 1,200 meters apart, okay? I also know that if Elena is at her house and she looks up to this antenna off in the distance, that her angle of elevation, so now we're getting into 3D, is 12 degrees, okay? So this triangle right here, this is on the ground, all right? That guy is kind of like a 2D triangle. These triangles that I'm outlining in red here, these are actually like up in the air because the antenna is now coming out from the ground, like my cup of pencils there. And these triangles are kind of like in the air triangles. Okay, so the other little thing, my jump in my common sense here, is telling me that if this antenna is made to stand up, and stand up over a good amount of time, it should be perpendicular to the ground, right? It should be at a 90-degree angle. So I think we can safely make the assumption that this antenna makes an angle of 90 degrees to the ground as well. Okay, and then we have this angle of elevation here as 12 degrees. Okay, so hopefully my model helps you. Thank you. I spent a lot of time on it. Okay. So here is what we are tasked to find. We are tasked to find the height of the antenna. So why don't we call that capital A? Capital A is our unknown. Okay, so sometimes in these questions we have to work with what we have, and we have to kind of work backwards to see what we need and see how we can maybe get that from other triangles, because some of these triangles are connected to one another. Like you see that the red triangle on the right over here actually has a shared line with our bottom triangle. Okay, this line between these two triangles are actually shared. Could that line be helpful for me to find the height of the antenna?
Yes.
Okay, because if I can find one side in this red triangle right here where I have the unknown A antenna, this side, this blue side right here, could be my key to be able to now apply a SOH CAH TOA trig ratio, right? So let's call this X. Okay, so we're just going to focus on our flat triangle right now.
So the base.
Yep, the base. And if I looked at this flat triangle in with a bird's eye view, it would have a right angle. This is Sam's house and Elena's house. It has 1,200 meters, 50 degrees, and we called this line, this blue line right here, we called this X. Okay, this is like kind of a bird's eye view of what we have. We also know, based on the picture, that this is a 90-degree angle. So could we find that? This is like opposite to 50, and this is hypotenuse. Which trig ratio should we use? Sine. So sine of 50 equals opposite X over hypotenuse 1,200.
I don't know how you did that. Why did you sign?
Because we're looking for opposite to 50, and we have hypotenuse, so I have to use sine. Okay? Okay, so we're going to multiply the 1,200 up. Alex, yep?
This is really confusing, but so we're trying to find the height of the antenna, but then we
Yep.
So if we had 1,200, we start with the bottom triangle, right? And
That's right.
We start with the bottom triangle, right?
Yep.
And then we just do sine 150 or 1,200 over sine 50, right?
Times sine 50.
Times 50.
Yeah. And that's going to give us this X. It gives us the connected line between those two triangles.
All right.
Okay? So we're working kind of backwards here to see what we need and what we can maybe get that the two triangles share so that I can find the antenna. So it's going to be a couple of calculations.
Wait, is this like one of those isosceles triangles?
Nope, this is a right angle triangle.
Could we not just do 180 minus 90 and 12?
Because of these. Is that what you're saying?
Supposed to find
So
the
these, remember that the triangles are like this, right? If the triangles are flat and I have two 90s, that can be 180, but as soon as we're one of these is going up into 3D, it's a whole different
Don't we know
thing.
that it's 12 degrees,
Yep.
so like 90.
So, yeah, we can get this, but that still doesn't help us get another side length, right?
Oh, trying to have a side like that.
Yeah. Okay, so what do we get? 1200 times sine 50?
919.3.
Okay. 919.3. Give me like one more decimal there until we get to the end. Or maybe we'll leave like 4 decimals till we get to the end. What do we have?
Usually it's 2 5, so I just did 3.
Okay, 25 what?
2 5.
Okay, that should be enough. I'm not going to round this just yet because we're using this to calculate another element. So I don't want to round too much. Okay, now taking this triangle that we have that's up in the air, this is the antenna. We're making the assumption that the antenna meets the ground at an angle of 90 degrees, that it's perpendicular. And this is Elena's house over here. We found that the angle of elevation, when she looks up to the top of the antenna, is 12 degrees. This is that shared blue line. That's our x that we actually just found. So if I know x equals 919.253 meters, I should be able to utilize a trig ratio here to help me find side A. 12 is my reference angle. What is A? A is opposite. X is adjacent. So, sorry, I heard it back there. Tan. Okay, so tan of the reference angle, 12 degrees, is equal to
9.
the opposite side, angle, or antenna A, over the adjacent side.
I'm so
Yeah.
confused. What are you doing?
I am solving for A in this triangle right here, this guy.
What's the tan thing? Is that like a cosine law?
So tan is like SOH CAH TOA. We're using SOH CAH TOA. So we're not using sine law or cosine law. We're using, because these are right angle triangles, we're just using the laws. Or SOH CAH TOA, sorry.
Opposite.
Yep, so this one has a little bit more like problem solving involved, right? Okay. Yeah, Lauren?
Couldn't we have used sine law because if we know that angle is 90 and the other one's 12, couldn't you?
You could have applied sine law, but because this is a right angled triangle, I think SOH CAH TOA is just a little bit quicker and easier for us to do.
Use sine law and
You can, yep. But I'm just saying SOH CAH TOA is easier and quicker. We're more used to SOH CAH TOA, and because it's a right angled triangle, I'll just apply it. But you can use sine law and you should get the same answer. You just have to find this other angle right here. Okay, what'd you guys get? 195? Okay, so can we say 0.4?
The height of the antenna is 195 meters.
Right.
what if we're not able to break down this
I
question?
think the reason is that there's just
When I look at it, I don't see like ground.
yeah, like that. I can
I can see it, but only the picture.
Yeah, so some of the pictures that I have on your worksheet are a little bit better. This one is not a great picture, but I will try as best I can if I give you a picture to make sure that it's, you can always ask too, like is this one flat or is this one in the air, if you're not 100% sure. Textbook resource, stuff like that.
Do we have an example 5? Because